There's a number in physics that almost feels illegal, a number so precise that it sounds like a fraud. It's the electron's magnetic moment, specifically the tiny deviation called G-2. And the reason it's famous is simple. It's one of the greatest agreements between theory and experiment in the history of science. Not pretty good, not close enough. We're talking about precision so extreme that it's like measuring the distance from Istanbul to New York and being wrong by the thickness of a human hair. So what is G-2, and why does it matter? Let's start with the idea of a magnetic moment. If you put an electron in a magnetic field, it behaves like a tiny magnet. It has an internal magnetic strength, and it wants to align with the field. In simple quantum mechanics, you can imagine the electron has something like spin, an intrinsic angular momentum, and that spin creates magnetism. Now, a basic theoretical prediction says the electron's gyromagnetic ratio, the G factor, should be G equals 2. Exactly 2. That's the clean, perfect answer you get when you treat the electron as a simple point particle interacting with the electromagnetic field in the simplest possible way. But nature doesn't give you exactly 2. It gives you a value that is slightly bigger than 2. That difference, the tiny extra, is what we call A equals open parenthesis G minus 2, close parenthesis over 2. It's called the anomalous magnetic moment. And here's the punchline. That tiny anomaly is not a mistake. It's the fingerprint of quantum fluctuations. It is the electron revealing that even empty space is active. Because in QED, the electron isn't alone. The electron is constantly interacting with the quantum vacuum. It emits and reabsorbs virtual photons. The vacuum polarizes. Loops happen. Those processes are invisible to your eyes, but they leave a measurable imprint on G. So in one number, G-2 is like a scoreboard for the entire quantum world hiding underneath. If you can calculate it correctly, you've basically proven your understanding of QED at a terrifying level of detail. And if the calculation disagrees with experiment, that can mean something even more exciting. It can mean new physics. That's why G-2 isn't just a flex. It's a test, a precision test, a detector for reality. Now the question becomes, how do you calculate it, and why is it so hard? Because G-2 does not come from one simple interaction. It comes from a whole infinite tower of quantum corrections. And this is where Feynman diagrams enter the story as the main tool, not as decoration, not as art, but as an actual computation engine. To understand the calculation, you need one key idea. In QED, an electron interacting with a magnetic field is not just one clean event. It is the sum of many possible quantum histories. In the language of Feynman diagrams, you start with the simplest vertex. An electron absorbs or emits a photon. That simplest interaction gives you G equals 2. But then QED says, that's only the beginning. Now add the first correction, the simplest loop you can draw. The electron interacts with the electromagnetic field, but along the way it can briefly emit and reabsorb a virtual photon before completing the interaction. That single loop is the first quantum correction. And when you compute that correction, you get a famous result. The first correction to the anomaly is A approximately alpha over 2 pi, where alpha is the fine structure constant, about 1 over 137. This is already wild, because it means the anomaly is directly tied to the fundamental strength of electromagnetism, and it's small because alpha is small, so the anomaly is tiny, but not random. It's a structured, predictable deviation. Now, that one-loop result was first computed by Julian Schwinger in 1948, and it became a landmark because it matched the experimental trend almost immediately. But here's the deeper story. That one loop is not the end. QED demands higher-order corrections, 2-loop diagrams, 3-loop diagrams, 4-loop diagrams, 5-loop diagrams, and beyond. Each extra loop adds more complexity, more terms, more ways the vacuum can influence the electron. And you might think, why would anyone do this? The first correction is already close. Because the experiments kept getting better. Scientists improved measurements to absurd precision, which means theory had to keep up. QED became a race between two things: better experiments and better calculations. And Feynman diagrams became the battlefield. But there's a terrifying part here. The more loops you add, the more integrals appear. And those integrals often try to blow up to infinity. This is exactly where renormalization enters again. Because to compute G-2 properly, you must handle infinities correctly. The strange beauty is this. Individually, some intermediate contributions look infinite. But when you add everything together the way QED tells you to, including counterterms and proper renormalization, the final observable quantity becomes finite. That's not luck. It's a sign of a deeply consistent structure. Now this is the moment to appreciate what makes G-2 special. Most numbers in physics test a theory at a rough level, but G-2 tests the theory down to tiny corrections, tiny loops, tiny quantum ripples. It's a microscope for the vacuum. And the vacuum is not quiet. So when you compute G-2, you're not just testing electrons, you're testing the entire quantum system of fields that can affect the electron. And that includes more than QED, because the electron doesn't only live inside electromagnetism. At higher precision, other forces leak into the result. And that's where the story gets bigger. At first, you might think G-2 is purely electromagnetic. But as measurements became more accurate, physicists realized something. Other parts of the standard model contribute too. Not much, but enough to matter at extreme precision. So the total theoretical prediction includes several layers: QED contributions. These are the biggest part and the most precisely computed. Electroweak contributions. Tiny corrections from W and Z bosons and related effects. Hadronic contributions. This is where the real pain begins, because hadronic means the influence of quark-gluon physics, the strong interaction, sneaking in through vacuum effects. And unlike QED, the strong interaction is messy at low energies. So the QED part is clean and surgical. The electroweak part is small but calculable. The hadronic part is the fog. That fog is the main uncertainty in the standard model prediction. And this is why G-2 becomes a powerful probe for new physics. Because if your experimental value deviates from the standard model prediction, the first question is it truly new physics? Or is it uncertainty in the hadronic contribution? Now here's the Feynman-style perspective. G-2 is an accounting balance sheet. On one side, you have what the standard model predicts, a sum of all known contributions. On the other side, you have what nature gives you in the lab. If the numbers don't match beyond uncertainty, that gap is screaming. Something is missing. It could be a new particle, a new interaction, a hidden symmetry, or some effect not properly understood. This is why people got excited about results for the muon's G-2, which is a similar story but more sensitive to heavy new physics because the muon is heavier. But even focusing on the electron, the lesson is the same. Precision doesn't just refine physics. Precision can break physics. It can reveal cracks. Now let's connect this to what Feynman contributed conceptually. Feynman's biggest gift here is not that he computed one specific number. It's that his framework, diagrams, and perturbation theory made these calculations possible and scalable. Because without an organized diagrammatic language, the series expansion becomes unreadable. The diagrams turn chaos into a structured list. They tell you what to compute, how to compute it, and how each part contributes. And when you put the whole machine together, you get a prediction so accurate that it becomes almost philosophical. Reality is not just described by QED, reality is confirmed by it. Now, in the final part, we'll close the loop. Why does the agreement matter so much? What does it mean for the limits of physics, and why G-2 is still alive as a frontier today? So why is this one number such a big deal? Because G-2 is not a rough check. It is an ultra-fine test of consistency. If QED were even slightly wrong in its structure, the calculation would drift away from experiment quickly as precision increases. But instead, the prediction stays locked onto reality. That tells you something profound. QED isn't just approximately correct. It is correct in the way a machine is correct, down to many decimal places. And here's another reason it matters. This agreement depends on renormalization working. If renormalization were a fake patch or a mathematical scam, it would fail under extreme precision. But it doesn't. It holds. So G-2 becomes evidence that renormalization is not a cheat. It's a legitimate feature of how quantum field theories connect to measurable parameters. Now we can summarize the whole story in a clean chain. The electron has a magnetic moment. Simple theory gives G equals 2. Quantum vacuum effects shift it slightly. That shift is computed as a series of Feynman diagrams. Renormalization removes infinities and ties everything to measured constants. The final prediction matches experiment with insane accuracy. That's the scientific miracle. But there's a deeper takeaway. The electron is one of the simplest particles we know, and even it cannot be described without the vacuum. It is dressed by fields. It is shaped by fluctuations. It carries the fingerprint of empty space. So G-2 is not just about the electron's magnetism. It's about the fact that empty space has structure. Now, does this mean we're done? Not at all. Because as we push precision further, the standard model has to keep answering new questions. Are there tiny new contributions we haven't seen? Is there a deeper theory beyond the standard model that slightly shifts these values? Do our hadronic calculations capture everything correctly? This is why precision experiments are still one of the most dangerous tools in physics. Big machines like particle colliders smash things and search for new particles directly. Precision experiments do something more subtle. They look for new physics by listening for tiny inconsistencies in numbers we thought were settled. They hunt with silence. And G-2 is one of the sharpest ears we have. So if you want a final sentence to remember, it's this. The electron's G-2 is the universe admitting that the vacuum is alive, and then letting us calculate the exact size of that life. That's not just science. That's control over reality's hidden bookkeeping. And once you understand that, you see why Feynman diagrams aren't just drawings. They are the language that made this impossible precision possible. If you want the perfect next episode in this series, it's this. Feynman diagrams, how to read them like code. Because now that we've seen what they can predict, the next step is learning how they actually work line by line, how a picture becomes a number.